Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. My name is Dr. Aiman. I'm from the Department of Materials, Manufacturing and Industrial Engineering, Faculty of Mechanical Engineering, Universiti Teknologi Malaysia. So in this video, I will give you an overview of my research in computational biomechanics and show how it can be used as an engineering solution for bone-related disease. Okay, so let's start with the definitions of biomechanics. From the science point of view, okay, biomechanics is about applying mechanical principles to understand how living systems move and respond to forces. Okay, so for example, when you are running, your femur bone experiences compression and tension to stabilize your movement. Okay, so but that is in the case for healthy people. But in those with bone problems, things can be very different. Okay. On the other hand, from the engineering side, as a mechanical engineers, okay, we are used to analyzing stress, strain, and material properties, right? But why should we care about bones, joint, or medical devices? The answer is because of the challenges in healthcare. Okay, so actually there are many challenges in healthcare that related to bone biomechanics. For example, we have degenerative and metabolic bone disease like osteoporosis, osteopenia, osteoarthritis. Okay, and then we have a vascular or necrotic condition, okay, which is due to disruption of blood supply, okay, which can cause bone collapse. And then we have trauma and fracture related problems, okay, which is due to accidents, bone quality issue, and implant related factors. And finally, we have a bone tumor. But in this overview, I will focus on one case study which related to osteoarthritis, okay, and how computational biomechanics can help. Okay, so osteoarthritis happens when the cartilage, okay, that covering the joint wears down, and this problem actually affects millions of people worldwide. And in Malaysia, the cases are rising, okay, with our aging population. Okay, so when this happens, daily activities become painful, and our quality of life will goes down. So one of the treatment is total hip replacement surgery, where the damaged femoral head, okay, is replaced with an implant, okay, which consists of acetabular cup, liner, femoral head, and femoral stem. Okay, and in a cemented procedure, okay, a cement will place around the stem, okay, to hold it in place. Okay, so the cement will be, surrounded with surrounded this femoral stem and make it stable. Right. But actually, not all surgery succeed. Some patient needs revision surgery, okay, because of infection. Okay, so when infection happens, okay, the bacteria infect the area around the implant, and if this complication left untreated, it will lead to more serious health problem, and therefore a revision surgery is needed. Okay, so during the revision surgery, orthopedic surgeon is having a hard time to remove the cement, okay, that is strongly fixed to the bone, especially the cement that located deep inside the bone canal. And during this removal process, okay, any excessive force will lead to bone fracture, which is a much bigger problem, right? Okay, so this is where mechanical engineers comes in. Okay, so in order to solve this cement removal process, okay, we are proposing to reduce the cement length. So as you can see in this picture, there are several you know uh, model, right, of the cement reduction, okay, where we reduce the cement part by part, and we want to investigate whether this solution is possible, okay, compared to the standard medical practice, which is the Foley method. Okay, but the question is this idea safe? Okay, or will it hold as well as the standard full cementing? And to answer this question, we need to use the computational method. Okay, so before that, let's take a look at the limitation of traditional experimental methods in biomechanical studies. Okay, for example, by referring to our case, okay, we're proposing to reduce the length of the cement. So our hypothesis is that the shorter the cement, the easier the removal process, right? But if we use an experimental approach, okay, we at least need four cadaveric femurs for testing, right? Because we have four sample right here, right? The first one is this full cemented model, okay, and then we reduce a little, cement length at the bottom of here, and then another length, we reduce it to cement. So we at least need at least four femurs, okay, to conduct the experiment. So this is not very practical, right? Because first, there's limited availability of bone sample, and the natural variability between specimens affect research consistency. Okay, and secondly, since we are working with human tissue, okay, ethical barriers limit the scope and repeatability of experiments. And finally, experiments require expensive equipment, specimen procurement, and lengthy procedure, okay, which place a heavy strain on research budget. Okay, so with computational biomechanics, okay, we can run unlimited simulations at lower cost, faster speed, and with more control. Okay, so when we conducting a computational study, the main concern is how reliable is our model. In other words, how much can we trust the result from our computational model? So to ensure reliability, we need to validate the model with experimental testing. Okay, so here I will explain how we develop the computational bone model and perform validation. Right. So first, we scan a cadaveric femur using a computed tomography scanner, okay, which is a medical imaging device that use X-ray and computer processing to create cross-sectional images of bone and soft tissue. Then, the CT images are then imported into biomechanical software to build a 3D geometry of the bone. Okay, and next we mesh the bone surface, and after that, finally, we can replicate the loading and boundary conditions from the experimental setup and extract strain values at the same position as the strain gauge used in the cadaver test, as in the experiment. Okay, so finally, we compare the strain values from the computational model with the experimental data using regression. Okay, so once the model is validated, we can run simulations according to our research objective, where in this case, to study the effect of cement reduction. Okay, so after the validation, we simulated different cement length, and we come with a conclusion. So the result showed that the reducing cement length is possible without major risk to the bone performance. Okay, so this could help surgeons minimize fracture risk during revision surgery. And all of this, thanks to the advancement in computational biomechanics, we now can provide a new solution to improve hip replacement procedure. Okay, so before I end, let's remember the scale of the problem. Okay, by 2030, Malaysia elderly population will expected to reach 5 million. Okay, that means millions of people may face bone-related disease and need advanced treatments. Okay, so to the younger generation, let's work together as an engineer to contribute to healthcare and improve the well-being of our society. So if you are interested in doing your final year project in biomechanics, feel free to reach me. Okay, that's all for my research overview. Thank you very much for your attention. Assalamualaikum warahmatullahi wabarakatuh.